Hi, Mr. Richmond. This is your Integrated Math 1, Unit 6.2 Lesson Summary. Unit 6.2, we will be solving systems of equations using elimination. This is expanding on what we did in 6.1. In 6.1, we solved systems by graphing and by using substitution. Elimination will just be a third option for how we can go about solving systems of equations. You will likely want to use elimination when you have your equations in what we call standard form, x then y equal to a constant. So you'll see that the x's are in one column, the y's are in one column, and our constants are in one column. So for all three of the examples here, except for the third one, we're a little bit out of order. These are in nice, neat columns. And so elimination will work great for the way these are written, because in elimination we want to add the columns down and combine them into a new equation. If a variable was solved, say x was isolated or y was isolated, then you probably should go back and use substitution. In the last section of this chapter, we'll talk about how to decide on which one. So for now, let's focus on elimination. So the process of elimination is combining the two equations into one in the hopes that one of the variables will be gone, will be turned into zero, making it solvable. In some of the easier examples, that'll happen just from adding them down. But as we get to the harder ones, you might need to multiply an equation to change it to make it so it'll eliminate. So let's start by doing that now. We'll just add these straight down and try to combine them into a new linear function. Negative 3x plus 3x is 0x. Negative y minus 4y is negative 3y. 12 plus 3 is 15. 0x would be 0, so I can cancel that out there. And then I just divide by negative 3 and I can isolate for y. So you can see by eliminating one of the variables, it becomes solvable. Once I've found what one of the variables equal, I need to plug it back into one of the original two, not anything new you've done, one of the original two, and solve it out. So let's try plugging into the top one. Negative 3x plus y equals 12. Negative 3x plus a negative 5, which is minus 5, equals 12. Okay, and you should always plug these in parentheses, so actually I'll write it that way for now. So 3x plus negative 5, in case there is a coefficient to multiply it by, it's a good habit. Then you can rewrite it. I'm going to add the 5 over and divide by negative 3 to isolate x. So my x should be negative 17 thirds. Now, you might look at that number and think that fraction seems wrong, seems odd, but with systems you never know. So it's always important after you get the x and the y and write them as a coordinate, because remember our answers in this section are intersection points, so it's a coordinate where they cross, comma negative 5, to plug them back into the original two equations and make sure they work. So let's do that now. I'm going to plug this back into the original top equation. Negative 3 times negative 17 thirds plus a negative 5 equals 12. Negative times negative is a positive. 3 times 3 is just a 17. So it's 17 plus negative 5, which is 17 minus 5, which is 12. So it does indeed work for the first equation, the top one. We'll try for the bottom one now. 3 times negative 17 thirds minus 4 times negative 5 equals 12. I'm just plugging in x and y into the equation. And just in case we didn't see, that is what I did here to get the x. And then I just rewrote the answer. Multiplying there, 3's cross out, leaving me with negative 17. Negative 4 times negative 5 is positive 20. And this actually, second equation should be set equal to 3, not 12. And as you can see, there's a lot of opportunities to make a mistake right there. Just a copying error. I wrote down 12 instead of 3. So double check everything as you do these steps. Otherwise, it's a long process to do over. Negative 17 plus 20 equals 3. And if I simplify that, it does indeed work for both. So I'm verified that this is indeed the intersection point. And if I was trying to solve this by graphing, that'd be pretty tough to find. I wouldn't probably guess that by looking at a graph. This is why we want you to know how to find these algebraically as well, because you can get an exact answer. Okay, let's take a look at example 2. Same idea, we're going to do elimination. X's are lined up, Y's are lined up, constants are lined up. I'm going to look for a variable to eliminate, X or Y. X won't eliminate as is, but Y will. So I don't need to do any multiplying, I'm just going to add them together just like I did here. X plus 3x is 4x, 2y minus 2y is 0y, and 6 plus 2 is 8. As I simplify that, I get a nice easy equation. 4x equals 8. Divide both sides by 4, and x should equal 2. Now that I know what x equals, I'm going to plug it back in to one of the originals. So I'll write the top equation, and I will plug x in for it. And now I have another linear equation I can solve, this time for y. I'm going to isolate it by subtracting 2 to both sides, and then divide both sides by 2. And this time it worked out a little neater. Hopefully it's correct. We'll write that coordinate, 2, 2. And then I'm going to plug it in and check the original answer. Now here I wrote out all the work for that check. For numbers like 2, 2, I feel a little more confident doing that in my head, so I'll just talk it out verbally. 2 plus 2 times 2 is 4, so 2 plus 4 is 6. It worked for that one. Double check 2, 2 again. 3 times 2 is 6. 2 times 2 is 4. 6 minus 4 is 2. And check. So if it worked for both these, I have the correct solution. Those lines would intersect at 2, 2. Let's try one more that's maybe not in perfect order. So now I look and yeah, the columns are good. I have the x's in the same column, y's in the same column, constants in the same column, but my equal signs aren't really lining up. And it's important that everything lines up, even those equal signs. So I'm going to readjust this a little bit and rewrite this. So 2x minus 3y equals 7 is in the correct form. I'm good with that. But I would like x and y to be on the same side, the left side of the equation. So I would subtract 4y over to get a new equation for that one. Okay? To rewrite that one, that would now be 2x minus 4y equals 6. And now I've just rewritten my system in a better order. I haven't changed the system at all. Now I need to solve this. If I look, 2x plus 2x is 4x, they want to eliminate. 3y plus negative 4y is negative 12y, they want to eliminate. So I need to multiply one of the equations by a number in order to make them eliminate. And the 2x's seem like the easiest, because if I can just multiply one of these by a negative 1, I'm going to go ahead and multiply the bottom one by a negative 1, then it will make the equation solvable via elimination. When I do that, I suggest rewriting both of them. So the top one I didn't change at all. The bottom one's going to be multiplied by this negative 1, which has to multiply to both sides of the equation, so it has to distribute to all of that, and becomes negative 2x plus 4y equals negative 6. And now I've yet again changed the system for a third time now, but I have everything in a nice, neat fashion. All the columns lined up, x's together, y's together, equal signs together, constants together, and if I add them, something will eliminate. So there can be a good amount of work here just to set up what you want for the problem. 2x minus 2x is 0x, negative 3y plus 4y is 1y, 7 minus 6 is 1. And there was a lot of work there, but it was an easy process once I got the elimination done. So y equals 1, and now I need to plug it back into one of the original equations. I can actually plug it into one of these, but just to keep everything consistent, I'm going to just say always, let's try to plug it back into one of the actual originals. So 2x minus 3y equals 7. Let's make y 1, and I'm plugging that in for y, which changes it to 2x minus 3 times 1. 3 times 1 is 3. Now I can solve this equation, add 3 to both sides, divide by 2, and x should be 5 and y should be 1. And again, I can check that solution by plugging them in or by graphing the two equations if I want to do it that way. 2 times 5 is 10, minus 3 times 1 is 3, 10 minus 3 is 7, it does work. 2 times 5 is 10 on the left side. 4 times 1 is 4 plus 6 is 10. So it does indeed work for both. I have the correct solution. Now the only other thing that can happen to you in this process that you should be aware of, and just some tricks to think of, is you can do the same tricks we did before. Now I don't know for sure if these numbers will work. I'm just making some up. If you get decimals in a system, okay, before you even start the elimination process, you can multiply everything by 10 to slide the decimal places over. By doing that, you might get some more reasonable numbers to work with. Okay, especially if you don't want to work with the fractions. You can do steps like this, and then I can try to find my number I'm going to multiply by to eliminate it. Sometimes the numbers aren't real good. I look at these, they're not real nice. I'm going to go for 32, so I don't have to multiply both equations, which means I need to multiply this one by a negative 16 and distribute it to everything. And now the x's would be eliminatable. So you can see that some of the problems will be a little tougher, but we'll practice a lot in class. Okay? The other thing to be aware of is if in the process of trying to solve these, let's just say you had one like this, and you add them down, because things will eliminate, 0, 0, and then 18. So you end up with a statement. So the variable completely eliminates. This happened when we were doing substitution. You also saw this during graphing. When something like this happens, and it's not possible, that's yet again another no solution situation. So when it happens with equations, systems of equations, anything you've done where the variable disappears completely and you get a false statement, that is a no solution situation. So you could call it that and then classify it. So this can happen in the process of solving these. On the flip side, without making up an example, if instead it ends up producing a true statement, 7 equals 7, something like that, that is now a mini solution situation, and that is consistent. They're asking you to classify it. So the process itself doesn't change for problems like that. You still try to solve them via elimination. Just if your variables don't really ever solve out to a numerical answer, you just get a statement. Then if it's a false statement, no solutions. If it's a true statement, many solutions. All right, thank you and good luck.